expansion because we don't even need it. It all cancels out because it's an exponential. Something also to note about these stationary states that we have over here. Whoa, what's happening? Okay. Something to note about these stationary states that we have over here, this capital psi of xt equals psi of x and phi of t, they have definite total energy. What I mean by this is, imagine we have a Hamiltonian, and Hamiltonian just means the energy operator, denoted by h hat. In classical mechanics, the Hamiltonian would be p squared over 2m plus v of x, which is also equal to 1/2 mv squared plus v of x. That's where you're accustomed to seeing it, but in quantum mechanics we're going to write it like this because, as I said before, p is an operator. Remember? In quantum mechanics we're working with operators because we want to see how operating on a system affects its values, its eigenvalues, and affects its eigenstates, eigenvectors. Now in quantum mechanics we can expand this out because p is equal to h bar over I partial with respect to x. We can expand it out, square that thing. We get h is equal to, after we do the calculations, we get negative h bar squared over 2m partial squared over partial x squared plus v of x. Aha! Remember the time-independent Schrodinger equation? It was equation 1. Let me just remind you. This is what it looked like. And you can see, another way to write this is that we have h psi is equal to e psi. In fact, this is the simplified version of the time-independent Schrodinger equation. Because h, the Hamiltonian operator, the energy operator, is acting on psi to give you the energy. Now this is very, very, very important. When you act the Hamiltonian, the energy operator, on some function, some wave function, psi, what you get is the energy associated with it. And E was just a separation constant, now we're denoting it as the energy. And you get the same wave function back. It's not altering the wave function as Hamiltonian, it's just giving you the value of the energy. And this is quite remarkable. And you'll also find out, if you do the calculations, that the expectation value, the energy is just, the expectation value, of the Hamiltonian is just the energy. Okay? And similarly, the expectation value of Hamiltonian squared is just energy squared by the same argument. And if you want to find any standard deviations in the Hamiltonian, you're going to find that it's equal to 0. And this is what I meant by definite total energy. Because, remember, well, I will show this to you next lecture, but you will know that there's this thing called a uncertainty principle. Now, the uncertainty principle states that if you take the deviation in the x of the x component and you take the deviation of the momentum, it has to be less than or equal to h bar over 2. Now this is very important, but I will get to this next lecture, I promise. What I'm just saying right now is that over here we have a finite value that this uncertainty relation cannot go beyond. While here we have no deviation. That means the energy is always going to be definite. There is no probabilistic ways of energy, the Hamiltonian. While over here we cannot have a definite x and have a definite p at the same time. There's an uncertainty to it. I don't know if you understood that, but I hope you did. What I'm trying to say is that Energy is definite. There is no uncertainty. Once you have the energy, you know it for sure. While over here, for the uncertainty principle, we do not know the definite momentum and the definite position at the same time. Okay, I think I'm going to stop here and we'll pick it up next lecture.